largest landslide ever recorded in the history occurred in the Norwegian Sea, and leaving behind many questions. And we can think about whether this slide was triggered by an earthquake, or why did it has a very long run out. And I think it's like it is very mystery. And then I think it's by using the numerical analysis, hopefully that we can somehow get a better understanding of this mystery. And furthermore, when we look at how the engineer assess the risk of submarine landslides, typically they rely on the finite element analysis to assess the safety factor for the marine slopes. And if the safety factor is low, then they switch to CFD analysis to predict the impact of the debris flows on the offshore structures. And I can get quite a limitation because when I try to play with the CFD analysis, sometimes we need to know how much soil will be released, the velocity of the debris flows, or the specific mechanism, all before running the CFD simulations. So I think it should be a better way, and that's why we developed a couple of CFD-MPM models to simulate the entire process of the submarine landslides. And with this model, we can perform effective stress analysis, not only for the slope failure, but also for during the runout of the debris flows. And we can also get into how the seawater, the marine sediments, and the offshore structure interact with each other in every single stage of the submarine landslides. So to validate the model, we recently went to Japan to partner with the Port and Airport Research Institute. And the idea is to validate the model from the centrifuge experiment with the 9-meter diameters beam centrifuge. And what they did is they submerged the embankment in water, and then they triggered the slope failure by seismic loading using shaking tables. And what we see here is that we want to understand what is the influence of the permeability on the failure mechanisms. And we can vary the soil permeability by adjusting the clay content of the materials. For example, in case number 1 on the right, so the soil had 5% of the clay content, resulting in a higher permeability compared to the case number 2, where the clay content is 20%. And in the experiment, we see that in the case number 1 is a typical slope failure when the slope obtains a lower gradient from the red line to the blue line. But on the other hand, in the case number 2, the slope transition from the initial failure to the debris flows. And we really want to understand why we have so different failure mechanisms. So by looking at the excess water pressure, we can see that in case number 1, the soil was liquefied in the beginning and then very rapidly dissipated. The excess water pressure was dissipated. On the other hand, in the case number 2, the excess water pressure was dissipated much more slowly. So, and we also confirmed that using the CFD-MPM analysis. And the message here is that we found that actually a slow dissipation of the excess water pressure is very important to generate a longer run out of the debris flows. And also the liquefaction induced by seismic loading might not be enough to generate the debris flows. And we also want to investigate further the mechanism of the submarine landslides. However, using the physical model is not feasible because of the limited size of the soil containers. So we need to rely on the CFD-MPM analysis. And when we go to the field and we look at for the sand, Actually, the field investigation show that the sand flow slide is combined of two main mechanisms. The first one is the erosion at the soil interface as a green area, and the second mechanism is the retrogressive sliding. So by using the CFD-MPM motor, we can reproduce the sand flow slide for the soil with high permeability. And if you look at the simulation here, we can capture the erosion at the soil interfaces in the first stage, and it was followed by the debris flows and the retrogressive sliding in the second stage. And finally, when the seismic event stops, the erosion continues and the slope gradually obtains the finer gradient, lower gradient. And the reason why the erosion occurred because it combined the turbulent flow of the seawater and also the very low value of the mean effective stress. But when we look at the clay is quite different. For example, if you look at the seafloor near the Stuttgart slide, that's the slide I mentioned in the beginning. Actually, the spread failure is the main mechanism. And the spreads involve the breaking of the marine sediments into smaller blocks called horse and graben. And these blocks are tilted and displaced on a horizontal failure surfaces. And we perform the simulation for the soil with a low permeability, and we can reproduce the formation of the horse and the graben under the seismic loading. And this also confirmed that the seismic loading actually can trigger this type of the failure. But we know that for the clay or for the soil with a low permeability, sometimes shearing can induce a very significant change of the water pressure. For example, for the over-consolidated clay, the soil can dilate during shearing. And by incorporating the dilation into the constitutive soil motor, we can capture the change of the water pressure during the onset of shear band. And the dilation will induce a decrease of the water pressure and an increase of the mean effective stresses. And in summary, when we think about the Stuttgart slides, one of the main questions is what caused the debris flow to travel remarkable distances? And the previous theory emphasized the importance of the turbulent and hydroplaning mechanism as the main reason. However, we show that actually a slow dissipation of the excess water pressure also important to generate a long runout of the debris flows. And finally, when we want to understand the influence of the permeability, I actually see that the permeability really matters. In particular, if you have the soil with a high permeability, the sand flow slide is mainly driven by the erosion at the soil interface and the retrogressive sliding. On the other hand, for the clay with a low permeability, the spreading failure mechanism can be what we can see in the field. So, and it also supports the hypothesis that actually the Stuttgart slide could be triggered by an earthquake 8,000 years ago. So thank you.